Beautiful. Now, I would suggest writing down a few things. Mainly the things that are bolded might be a good idea. But who knows? Never know. Okay? Now, when we're talking about this entire chapter, it's all about the nucleus. Right? We learned there's three things in an atom. What are those three subatomic particles? Protons, neutrons, beautiful. Now, two of those are located in the nucleus. Which ones? Those two. Very good. Okay, and that's, if you think about it, when we're talking about nuclear chemistry, all we're focused on is the nucleus. Everything in this chapter is focused on the nucleus. Okay?
Is this 4 hard and half-life?
Are you good at subtracting 2? No. Are you good at subtracting 4?
Yeah.
Okay, that might be easy. Are you good at adding 1? Okay. Are you good at adding zeros? I'm just checking.
Sorry, Coach.
That's the negative on the zeros? That's today, pretty much. Okay, so there's 3 types. We are focused on number 1 right now. We'll get to 2 and 3 probably the end of this week, maybe next week. We'll see how that goes. Radioactive decay is what we're looking at today. Radioactive decay, and there's 3 of them. One is known as alpha, the other is known as beta, and the third one known as gamma. Alpha, beta, gamma. You probably heard of those 3 at some point, one time or another. Alpha, beta, gamma. Okay. This is what radioactive decay is. This is what it is. This is the definition. A process by which an unstable nucleus, once again, the nucleus, a process of the unstable nucleus emits particles and energy in order to change into a different atom. Well, how cool is that? It's kind of like the half-life. We just talked about half-lives. It decayed into a new atom. That's exactly what this is. We're emitting energy in order to change into a different atom. Wow, it's kind of like deja vu. Did we already learn about this? Deja vu. Spell that.
D-E-J.
Yeah.
A-V-U.
That's actually pretty impressive. That's deja vu. Okay? And that's radioactive decay. Okay? Unstable turns into stable. Beautiful. Beautiful. And we'll go over how it does that. Okay? Everybody good? All right. Now, there are 3. One is called an alpha decay. Now, an alpha decay, it's the strongest, but it's at the same time it's the weakest. How cool is that? All right. So an unstable isotope emits 2 protons, 2 neutrons in the form of a helium nucleus. Okay. So when we look at an alpha, the alpha particle we always write as 4,2 helium. It's always a 4,2 helium. That's what it is. That's an alpha particle. Now, the top number represents the mass. Okay? So the top number is the number of protons plus the neutrons. Protons plus neutrons. Where the bottom number is just the atomic number, which is equal to the number of protons. So how many protons does helium have?
2.
2. What is it on the periodic table? How clever is that?
That's very clever.
Okay, so if it has 2 protons, 2 plus what number equals 4? Helium has 2 neutrons as well. And that's why we say 2 protons and 2 neutrons. Okay? Now, an example of an alpha particle. This is where we got to subtract. We got to subtract a little bit. The example I gave was 240. 94. Pu. All right. Now, when it undergoes an alpha decay, okay? What's alpha again? What's my alpha particle?
It's 2, 4.
4, 2. Helium plus some answer. Okay. 4, 2 helium plus some answer. Okay. Gotta do some math. Okay. What's the opposite of adding 4? All right, so we gotta subtract 4 on both sides. So that cancels out, that cancels. All right, what's the opposite of adding 2? So let's subtract 2 on both sides. Subtract 2 on both sides. All right, here we go. 240 minus 4. 236, that's what I'm talking about. Okay. 94 minus 2. 92, that's what I'm talking about. Okay. What element would this be? How would we know that? What element would that be? So helium's 2. What element is 92? Uranium. It's element 92. Okay. So how you can view this, a different way you can view this is instead of subtracting, because sometimes subtracting is a little difficult. Okay. Another way you can view this is like my arrow. My arrow is kind of like an equal sign, right? My arrow is an equal sign. 2 plus what number equals 94? Is that an easier way to look at it? Harder way? 2 plus what number equals 94? Well, 2 plus 92. 2 plus 92 is 94. Just giving you different options to look at it. Yeah, different options. That's an alpha particle. Okay. Another example down here, if you look, 222 is equal to 4 plus 218. And then the bottom, 88, is equal to 2 plus 86. How cool is that? Okay, let's look at beta. Beta is represented as 0, -1. I like to give it an E. 0, -1. -1. What in the world does that mean? 0, -1, E. Right. We got this. So if I start off with a 222 over 88 RA, and it undergoes a beta decay, what is my final answer? Okay, so let's check this out. Remember, my arrow is like an equal sign, right? My arrow is an equal sign. Okay. Jordan, how you doing? Question for you. 0 plus what number up top is equal to 222? That's what I'm talking about. That's what I'm talking about. Let's see, Christian. I got -1. What's the opposite of -1? So we got a positive. We got cancel that out. +1. What would that turn into? 89. There we go. What element is 89, Darius? What's my symbol for 89? AC. Beautiful. And that's how you do a beta decay. Any questions on that? Here's another example down here. If you look at this example, okay, here's my beta particle. Okay, there's beta. 0 plus 14 is 14, right? 7 plus a -1, which is kind of like minus. 7 minus 1 is 6. How cool is that? Now, those two are a little difficult, right? Gamma is my favorite because gamma's kind of like the ghost. You don't see it coming. You know when my door like somehow opens and no one's there? That's gamma. It's coming in. Gamma the ghost. He just kind of comes in whenever he wants. Because why am I saying this? You probably think, Mr. Rogers, you're a little crazy. No, I'm not. Because gamma is a 0, 0, y. Gamma is 0, 0. There's no mass. There's no charge. So how in the world do we know gamma's even there? That's the question. How do we know it's there? And the only reason we know is how deep it penetrates. And it's really fascinating. Because it only pairs with alpha and beta. You will never see gamma by itself. You will never see a gamma by itself. Okay? So let's see. Kind of ran out of space a little bit. But if we look at this problem, I have a beta, right? That's beta right there. I have a gamma, and then it's going to create a new element. So I have my beta, my gamma, new element. All right, let's see. Dawson, how are you doing?
Good.
You ready?
Yeah.
60 is equal to 0 plus 0 plus what number?
6.
Beautiful. Beautiful. Okay. Let's see, Shelby. What's the opposite of a -1? 1. So I got a +1 to both sides. Okay. That gets up to 0. All right, so 28 is equal to 0 plus 0 plus? Beautiful. Aiden, what element's 28 on periodic table? What's the symbol? Ni. Beautiful. And that's what a gamma looks like. Right? Gamma, it doesn't add anything. It's just kind of there. Okay? Bless you. Okay? That's what gamma looks like. Okay? Here, gamma is paired up with an alpha particle. How cool is that? Okay? Just another example. Cool. Any questions on gamma? Last slide. This is a summary of what alpha, beta, gammas look like. Okay? We know the symbols. We know the symbol for alpha is that. We know beta is that. And we know gamma is that. Okay? The mass. Well, we already know the mass because the top number tells us the mass. So the mass of alpha is 4. That's where we got 4. The mass of beta is 0. And the mass of gamma is 0. Okay? Cool. Cool. Now the charges you'll have to think about a little bit. When we think about this, what's the charge of a neutron? Neutral. Very good. What's the charge of a proton? What's the charge of a proton? Positive. Very good. And that leaves electrons to be negative. So if I look at this, I have 2 protons, which are positives. I have 2 positive and 2 neutrals. So my overall charge is 2 positives. Okay? And beta, I lose a proton. When you lose a positive, you go down 1. And that's why you go down 1 in the charge. Okay? Very interesting. Now, the penetrating power, I'm going to try to get a virtual lab that we can do tomorrow. We can't really do all that because it's nuclear radiation, and nuclear radiation isn't the best.
It's not good for you, is it?
Probably not that good.
It will be fun.
And yeah,
You can put it on the drill. Being like chain, well, like, what is it? Morph into like some alien.
that'd be interesting. Yeah. Okay. But penetrating power, alpha is the least penetrating. It gets stopped by your clothes. Your clothes can stop it. Beta can go through your skin. It can go through your skin, but usually gets stopped at the bone. Okay? Where gamma is like an X-ray. All right? It can go through your body pretty easily.
Your gamma theory, man.
It could easily. Now, why do you think when you get an X-ray, you wear? Has anybody ever gotten an X-ray before? Why do you wear a lead plate or a lead vest? You don't get radiation.
So if the radiation doesn't creep into your body and start yelling at you.
You're exactly right. Okay? So, what I have to show real quick, I have it pulled up. Have you guys heard of Chernobyl?
Yeah. It exploded.
It did
And
explode.
a bunch of people are dead.
Yeah, I know about this.
But now there's animals there. I watched a video on it.
There's a full documentary. It's pretty cool. I think it's on Netflix. It's like an hour long. I'm not showing an hour long video.
We should watch it tomorrow during
It's the whole city that's like Ghana.
The
It's
whole
like,
shit-
it looks all futuristic, kind of. Like, old futuristic.
So this is a fission reaction. Reactor that blew up.
Numbers 4. It melted down on April 26, 1986.
Oh man.
So what happened was so much heat was generated inside that reactor that it basically blew the top off, spreading radioactive isotopes throughout this whole surrounding area and over into.
We missed the beginning of that.
That is Chernobyl nuclear reactor number 4. It melted down on April 26, 1986. So what happened was so much heat was generated inside that reactor that it basically blew the top off, spreading radioactive isotopes throughout this whole surrounding area and over into Europe.
So that's called a Geiger counter. Okay, the Geiger counter tests radiation to see if alpha, beta, or gamma particles exist.
And that is why we can still detect the contamination to today. and they covered it in that sarcophagus, which is kind of crumbling as it ages. And so they're actually building a brand new containment facility over here, which, when it's finished, will be slid over on top of the old containment, on top of the old sarcophagus. The town of Pripyat was built just a few kilometers away from the reactor, mostly to house the families of the people who worked there. And now it is completely abandoned. So now you can find all of these high-rise Soviet apartments completely empty and crumbling, and the forest is basically reclaiming this whole town.
There's like deer living in the hotel room.
When the residents of Pripyat were told to evacuate, they were told that they would only be away for 2 weeks. So they left most of their belongings exactly where they were, and they never came back. So their lives are on display here.
Like a scary movie. I'm just kidding. Right?
I'm inside an old kindergarten, and it's incredibly peaceful. You know, you look around and it looks like a disaster has hit here, but mainly what this shows is 30 years of weathering, no maintenance. So things just fall apart.
It's crazy how 34 years later, those objects still have radiation. 34 years later.
The most insidious thing about radiation is how invisible it is. You can't feel it, you can't smell it or see it. This could be pristine wilderness, but it's not. It's a contaminated, deserted wasteland. This is what a real post-apocalyptic world looks like. Abandoned buildings, overgrown streets, everything crumbling, rusting, breaking. Near the reactor, there's an area called the Red Forest, because after the accident, so much radioactive material was dumped in that area that all the trees died, and their leaves turned red, just like they do in autumn. I'm standing on the stage of the Pripyat Theater. Something about this place that just, I can picture the scene. I can picture it here. A packed house. All the great Russian productions that were staged here. And you're looking around at all the old lights and the layers upon layers of walkways they would have used. This is a pretty amazing location. This is my favorite place so far. Nothing radioactive. It's just an amazing look at the past of this place.
He just kind of walks around the town. The second most radioactive place on Earth. The second most. The first I always forget the name of it. It's in Japan, I think.
He's just walking around.
He is. Well, he always has a Geiger counter with him to see where he can go and where he can't go. But the second most radioactive place is actually he suited up because he found a hot spot. It's actually in the basement of the hospital. So the hospital at Chernobyl, the basement is where the firefighters after the explosion were located. Okay? And they all died. And their fire suits are all in the basement of the hospital there. And that's the second most radioactive place on our Earth. That's pretty crazy. All right. So, pretty sad story, actually. But it's just shows you how radiation can kind of sneak up on you, right? And that's why we don't really do any labs on radiation. So we still got about 10 minutes left. I'm going to give a little practice of alpha, beta, gammas. So I want you guys to try this out. It is front and back. Give it your best shot. I feel like we got a good chance at this. Then we'll move on. All right. So try this out. Get as far as you can. Might not be able to finish today, and that's absolutely okay. Front lights coming on. 3, 2, 1. Back light. 3, 2, 1. All right.
You get the string and pull it all the other one's way more. Yeah. I just saved your life. All right.